Deep in the heart of the cosmos, the life of a massive star approaches a violent conclusion. Gravity begins to win its eternal tug of war. The core collapses in mere milliseconds. And from the ashes, something entirely new and much more mysterious is born. At the heart of every black hole lies the singularity, a region where matter is crushed to a point of infinite density. In the fabric of space-time, this appears as an infinitely deep gravitational well. It is a mathematical boundary where our standard laws of physics cease to function. Density is mass divided by volume. As massive stars collapse into the smallest possible space, the volume approaches zero, sending density toward infinity. This collapse defines the singularity, the ultimate endpoint of matter trapped within the event horizon. At the heart of every black hole lies a boundary from which there is no escape, the event horizon. Consider it a cosmic point of no return. Even light, the fastest entity in the universe, finds its path bending inward once it crosses this invisible threshold. Once inside, space-time is warped so severely that all paths lead directly to the singularity. The laws of physics as we know them cease to apply here. As an object crosses the threshold into the intense gravity of a black hole, it encounters extreme tidal forces. The gravity at the front of the object becomes significantly stronger than at the back. This difference in gravitational pull results in a phenomenon known as spaghettification. The object is pulled into a thin, elongated strand, ultimately becoming part of the accretion process. Gravity affects more than just space. Near a massive object like a black hole, the fabric of space-time itself warps, causing time to slow down. Consider two identical clocks. One remains at a safe distance, while the other drifts near the event horizon. As the second clock approaches the intense gravitational field, its passage of time appears to drag significantly. This phenomenon, known as gravitational time dilation, reflects the same frequency shifts we observe in light. Time and light are inextricably linked to the curvature of our universe. To peel back the mysteries of the cosmos, we rely on our most powerful observer, the James Webb Space Telescope. Operating far beyond the reach of human hands, it serves as our eyes into the deepest reaches of space. Deploying such a massive instrument required a complex, multi-stage process. From its folded state inside the launch vehicle to the precise tensioning of its sunshield, every movement was critical to its success. The heart of the telescope is its massive array of gold-coated hexagonal mirrors. This unique design allows the telescope to capture infrared light with unprecedented clarity and sensitivity. By gathering this ancient light, Webb allows us to look back in time, answering fundamental questions about the birth of stars and the formation of galaxies. Every stunning image from space starts as a FITS file, a complex data structure containing raw photons captured by telescopes. Through sophisticated pipelines, raw sensor inputs undergo arithmetic processing, translating abstract binary values into visible light wavelengths. This workflow reveals intricate dust clouds and colors hidden away until the final visual synthesis is complete. Just 4 light-years away lies our closest stellar neighbor, Proxima Centauri. This system contains a world that has captivated astronomers, Proxima b. Proxima b orbits within the habitable zone of its parent star. But because Proxima Centauri is a red dwarf, the planet experiences extreme conditions, potentially including tidal locking. What does a world like this look like? Spectroscopic data suggests a harsh environment, perhaps filled with volcanic activity and a landscape stripped by intense stellar radiation. Proxima b remains one of the most significant targets in our ongoing search to understand if we are alone in the universe. In an age where AI can generate hyper-realistic space imagery, visual literacy is no longer optional. Distinguishing between a simulation and a scientifically grounded visualization is the key to true understanding. Visual literacy involves a layered process, defining needs, interpreting data, and evaluating sources. These functional pillars ensure that the science stays at the forefront. Whether through complex charts or holographic data models, effective visualization must be rooted in raw telemetry. Data integrity is the difference between a creative rendering and scientific fact. When we see visuals backed by JWST or NASA mission data, they earn the mark of authenticity. Grounding our cosmic mysteries in verifiable source data bridges the gap between hallucination and discovery. At the heart of the cosmic mystery lies the midpoint climax, a colossal collision of galaxies. Here, gravitational tidal forces act like invisible hands, tearing apart the spiral arms of two massive structures. These interactions, stretching across hundreds of thousands of light years, are not instantaneous. They are epic dances that span billions of years, reshaping the very fabric of the deep cosmos. By mapping the stellar gas and dust, our sensors reveal the distortion caused by this immense gravitational pull, creating long, sweeping tails of stars that drift into the dark expanse. This chaotic transformation is a testament to the immense power of gravity, turning isolated galaxies into a new singular structure. The universe is full of mysteries. Subscribe for more cosmic explorations to continue our journey into the unknown. We are entering a new era of propulsion. Ion engines use electrical fields to accelerate ions, providing high efficiency for long-duration deep space missions. Looking ahead, theoretical warp drives aim to manipulate space-time itself, bending the fabric of the universe to bridge vast interstellar distances in a fraction of the time. When we gaze out into the abyss, we are not just observing the universe. We are looking back at our own humble origins. From this vantage point, our home is nothing more than a pale blue dot suspended in a sunbeam, fragile and solitary in the grand cosmic expanse. Every war, every triumph, every life we have ever known exists on this tiny speck, reminding us of the profound responsibility we share to protect it. As we push the boundaries of knowledge, we don't just learn about the stars, we learn what it means to be human. The universe is governed by the second law of thermodynamics. Over eons, order decays into disorder and energy spreads out, leading towards a state of maximum entropy. For billions of years, the cosmos is a vibrant place, fueled by the birth and death of stars. But even this cycle is temporary. As time progresses, fuel is exhausted, stars flicker out, galaxies dim, and the universe enters a long, silent twilight. This is the heat death. Ultimately, the universe reaches a state of near-perfect cold and darkness, where no more energy can be harnessed for work. We began at the heart of darkness, examining the singularity, where gravity distorts space and time beyond human comprehension. From the infinitely small, we zoomed out to the infinitely large. We traced the filaments of the cosmic web, the invisible scaffolding of dark matter that shapes our universe. Finally, we charted the timeline of our existence, a 13.7 billion year journey of expansion, from the initial Big Bang to the complex, accelerating cosmos we see today. Every concept acts as a piece of this vast puzzle. Synthesizing this knowledge allows us to look at the night sky and see not just stars, but the history of the universe itself. Despite our breakthroughs, the universe remains shrouded in mystery. Dark energy, the potential for a multiverse, and our very existence in a matter-dominated cosmos stand as the ultimate frontiers of human knowledge. The mystery is not just out there, it is part of us.